Yes. Well, the point is, once you have fixed the future to be going up on the one side, right, it will be going up on also on the other side, because the notion of future, right, you cannot, it has to be continuous, right? Let me draw that picture again. So you have so here the future corresponds to going up, and we know that the time-like curves will lie within 45-degree angle of the particle, right? So once you have defined the notion of future here, right, you can continuously change, right? And the notion of future here will be like this. In terms of the t coordinate, t will go down because t goes to minus t, right? So the notion of future is increasing t. You have taken it to be increasing t on this side. That's our convention. Then there is no choice, but in this side it will be decreasing t. Yes. 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 Yes, true. Okay, the point is, imagine that a person here, right, falls into the black hole, right, crosses the horizon. Suddenly the notion of future cannot change, right? So to an observer here, the notion of future will also be looking like this, right? If somebody comes from the left hand side and meets inside, it better be the notion of future is the same for both, right? So unless you take the future to be upward directed here, okay, these two people will not agree about what the future is, right? So once you have fixed the notion of future in one region, right, there is no choice. You can just continuously go to another region, and the notion of future has to remain the same. Yes. So you could have chosen, you could have said that I'll fix the notion of future on this side. Then it is fixed everywhere. It will be downwards. Right? But once you fix the notion of future in one place, in the whole space time, you don't have a choice of anywhere else how to fix the future, right? It will be the same upward direction. Otherwise, there will be disagreement, right? Between two. No, there is no disagreement because nobody told you beforehand, right, that this t, increasing t, is the future. That we chose. We said that our time, right, what you are observing, is going upwards. Right? So what it is saying is that this future over here, right, should also be going upwards. Right? It's that so basically the point is from this observer's viewpoint, right? Minus t is the time, not t. Right? It's a change of coordinates. We could have done it in our space time also, right? Instead of t, we could have used minus t as our time. Right? The metric will remain the same, right? Because there is a dt square. Which solutions? Yes.
So do they tell us directly what happens after the 2GM boundary, or are we just like reasoning, like making zeros once they have crossed the boundary?
Yeah, because the point is this is not any spatial boundary, right? Because as I said, we could be falling through the horizon of a big black hole, right? We wouldn't know. So there's nothing spatial going on here, right? So it's not a sharp boundary in any sense. So if our notion of future is upward directed, right, we may decide to fall in, and suddenly the notion of future cannot change as soon as we cross the horizon. Right? It has to remain upward directed. Yes.
I don't understand why we have surface of a star is collapsed in rho coordinates, rho is decreasing. At the same time, two simultaneous solutions in this r prime coordinate. So why can't both the solutions exist simultaneously when both this region of the space are disconnected from one?
Yeah, both solutions may exist separately, right? But there will be no connection in between,
Yes.
right? There will be like two different black holes, which are collapsing in two different parts of space-time,
Yes.
right?
But there is notion of time in both the regions are also both the solutions.
No, because no, I mean the question is what is yeah. Notion of future. Suppose a black hole is collapsing here, and a black hole is collapsing here, right? The same notion of future in both cases, right? It's just that to connect them inside, right? The T of this gets connected to minus T of this, right? That's all we are saying, right? Not that the notion of future is different, right? See, the point is if the two black holes are collapsing individually, right, then there may not be any connection in between, right? It's just that one black hole is collapsing here, another black hole is forming there, right? They're completely independent objects, right? To be able to make that connection, right, we have to use the maximally extended Schwarzschild geometry, right, which is not physical because this maximal extension assumes that there is no matter anywhere, right? Whereas as you saw, if it forms out of the collapse of a star, right, there will be matter inside, right? And you have to take that into account. Once you take that into account, the maximally extended geometry is not the correct geometry, right? So for a real collapsing star, this question doesn't even arise, right? What is the correct time? Because we only have one side, right, outside. If you take the maximally extended solution, right, then this question arises because you have to fix a future, and once you have fixed a future in one region, the same notion must continue everywhere. And it's just that, I mean, if you look at the solution, right, here increasing T is the future, here decreasing T will be the future, right? Because as you go up, T actually goes down in this region, right? Because T is minus T of that side. So that just means that you have chosen the wrong time coordinate, right? The T is not the correct time coordinate for on that side, right? You should have chosen minus T as a time coordinate on that side. Yes.
These guys will one day will go this way, other day will.
But increasing T being the future, right? We'll see that there is a problem with that. I mean, we will see what the problem is, right? The T cannot be thought of as a global time everywhere. Right? I mean, see, increasing T being that the future everywhere means that you are thinking of T as a global time coordinate, right? But we will see that that cannot be, that is not possible in this geometry. Right? T is a wrong coordinate. I mean, you already know that rho T is not the correct coordinate system, right? It's valid only outside, right? You have to change coordinates to go inside, right? And we will see explicitly that once we map out the rho T space, right? Constant rho and constant T surfaces to in the I prime T prime plane. Yeah, we have other solutions, many other solutions, right? So this is a general class of solutions, the black hole space time, right? Schwarzschild is a special case, the simplest one. Then you can have charged black hole, right? Which is spherically symmetric, but it carries charge. Right? And then you can have rotating black holes, right? Which will not have the full spherical symmetry, but only the azimuthal symmetry. And then the most general one that is known in 4 dimensions is a charged rotating black hole, right? You can add charge and rotation, which are much more complicated solutions.
You always see the rho equals 0 in the left.
Yeah, except that the rho equal to 0 singularity, right? Here we saw that it's like a what is called a space-like singularity, right? Because it extends in the space direction, right? In time, you hit the singularity, right? But in other geometries, it's not the case, right? I mean, for example, once you put charge, right, you find that these things are become time-like, right? They become vertical instead of horizontal. Okay, so that the details of the singularities change, right? But there will always be some singularity at rho equal to 0.
For rho greater than 2gm, and increase in direction of T prime is we are agreeing that there is also similar to increase
Yeah, that is our convention. Let's suppose that we have decided that this t at infinity is the correct time, right? Then increasing t is future, right? And that we saw coincides with increasing t prime.
Once we cross the horizon, what exactly is happening? As we increase t prime, still the notion of t is there, and t is really increasing. Because when we look at Schwarzschild, we can see a
yeah. So once you cross the horizon, right, then t is not the time coordinate anyway, because it becomes a space coordinate, right? Because the sign changes. Okay? So you cannot say that increasing t is time future. The increasing t has a space-like direction, right? But increasing t prime being the future is okay, because if you look at the metric, let me write the metric. Okay, let me also write the coordinate changes. Okay. So the point is that the t is not the time coordinate anymore, because it's 1 minus 2 gm over rho, right? That becomes negative once you go rho less than 2 gm, right? So you cannot say that increasing t is future. But t prime is still that time valid time coordinate, right? Because its coefficient is minus dt square, right? So you can choose t prime to be the time. And now the point is, once you have decided that t prime increasing is the future, right? That because far away t prime increasing is the same as t increasing, and that we chose as our future. Then we can continue this definition of t prime increasing as the future everywhere, right? Because t prime is the time coordinate globally, right? It can be treated as a global time coordinate everywhere in space time, right? So, in other words, I mean, you have this cone, right? You have the light cone, right? And you have to decide between these two cones whether this is the future or this is the future, right? And the point is, once you have decided that this is the future, you have no choice to make this future anywhere else, because you can continuously connect the space time, right? So everywhere this upper cone will be the future, right? Which is the direction of increasing t prime.
whenever we say about inside event horizon, we are mentioning to the upper part of that. If you look at the lower
Yeah, but the point is, lower part is not physical, because for a collapsing star, the lower part doesn't exist, right? That's why you are focusing on the upper part. But indeed, the lower part is also there, right? If we the fully extended geometry, the lower part is also there. Okay, is that the lower part is not there when you have a collapsing star. When this is formed by a collapsing star, then it's only the upper part that is important. That's why I am referring to the upper part as the event horizon. Because the star, right, the falling star goes like this, right? So below this surface, right, the solution doesn't changes, right? So that's the sense in which the lower part doesn't exist, right? Because anywhere beyond this, okay, we cannot trust the solution. People have solved, yeah. I mean, assuming, I mean, some simple geometry, right? Simple shape of the star, for example, a spherical shell of collapsing matter, right? Where all the mass is concentrated on the shell, right? With that, people have solved. Inside it will be like a Minkowski space, right? Because its R mu nu equal to 0, but there's no source of particle, right? So it's like what happens in Newtonian gravity, right? If you have a shell, right, outside there is gravitational field, but inside there is no gravitational field.
inside the spherical shell, we have to take consider the fact that the boundary condition, like,
Yes. So you have to, I mean, earlier we didn't need, right? Because we solved in flat space time and the solution fell off at infinity, right? It went to asymptotically Minkowski space time, right? Here, of course, you need boundary condition because if you are solving inside a spherical shell, right, you have to understand what happens at the boundary of the shell, right? And there is a jump in the derivative of the metric, right? Because of there is a delta function mass distribution on the surface. So that you have to take into account.
so like far from the shell, but as we go near the boundary, stay.
I think it, if I remember correctly, it stays Minkowski. That it basically remains flat space time inside, right? And there is basically, so you have Schwarzschild geometry and then flat space time geometry, right? Pardon?
And there is jump.
There is jump, exactly, right? But okay, this I'm not completely sure. You can look up the literature, right? What happens if I have a collapsing shell of matter? Yes. Any other question?
I have one general question. Started solving it,
Hmm.
basically assume that these are like some coordinate system that
Yes.
and somehow we assume that it's R4, right?
Is?
Topologically, it's like R4 because we can parameterize our.
Yes. Yeah.
But I mean, how do we know for sure that this is the only kind of solution? Some other.
Yeah, yeah. There can be other solution. They'll just not describe what we want to describe, right? We want a concentrated mass. You wanted a concentrated mass in Minkowski space time, and you want to know what its field configuration is, right? So far away, it should go to Minkowski space, and I mean that's the solution we got. Yeah, as using spherical symmetry, etc. Right? Time independence, for example. Right? Otherwise, you can support gravitational waves on this background.
That's why we are saying that it should be constant.
Yeah, or you don't want to decrease the mass sufficiently far away from the source, it should go over to flat space, right?
Assuming that far away close to flat because it's space time. This is not the only possible type of solution. There can be other.
If you want spherical symmetric solution.
Spherically symmetric is the only one. But if we
yeah, you can certainly find other kind of solutions, right? This is not the unique solution to general relativity, right? Otherwise, the subject would have been over, right? Classical general relativity. So certainly there are a lot of solutions you can construct, right? Including gravitational waves that we'll be studying later. Cosmological solutions, for example, right? Time-dependent evolution of the universe. Yeah, spherical symmetry and time independence, right? Those are the two assumptions we put in, right? And that there is no mass distribution in space time, right? With those conditions, it's unique. Because those are the only things we use, right, in solving it.
mass distribution is even further, right? Because those are not static.
Exactly. Yeah, yeah. So certainly, I mean, even in Newtonian gravity, right? If you have to solve for the gravitational field due to a mass distribution, right? Then it will be a much more complicated problem, right?
Is there any no other resource other than?
Yeah, typically you have to do numerics. If you want to do, for example, black hole merger, right? Which you can model by 2 point masses moving around each other. You have to solve it numerically, the equations. Right? There are approximations you can use, right? But if you really want to solve it fully, you have to use numerics.
Keeping t equals to minus t symmetric by using these two black holes.
No. These are describing that there can be two independent black holes collapsing, right? So that is different, right? That is not that their interiors are not connected, There t is a time coordinate for each outside, right? Each will have a geometry like this, will be described as geometry like this, but the interiors may have nothing to do with each other, right? What we are saying here, that if you consider the maximally extended short shell geometry, then the t here, right, is the time coordinate chosen so that it's future directed. In that case, here the time coordinate that is future directed is minus t. Okay, that's all that is in the statement. That you have to use minus t as the time coordinate here if you want the future directed time coordinate. But if you just look at the Schwarzschild solution, right, then t goes to minus t is the symmetry of the matrix. So whether you call t as the time or minus t as time is up to you, right? Okay, it's just that once you have this connected geometry, right, then it's up to you in one region what to describe as the future, right? In the other region, it's not up to you. Once you have decided that t is the time coordinate, future directed time coordinate here, then minus t will be the future directed time coordinate in this region. Right? That's all the statement.
These two regions are not accessible through timeline curve. Are they still connected?
They are connected because you decide what is future here, what is future here, right? Throw the two observers into the horizon. They can meet and they can compare that time, right? And they better agree what is future, right? So they are connected in that sense, right? Even though you cannot go from one to the other region. Because between any two neighbors, there is a connection, right? Because you can see this space-time, there is no singularity inside, right? So inside it's a continuous space-time. So you can certainly go between one point and the neighboring point. Okay, so with this, so you have the equations already. Okay. So what we are going to do now is to first plot the constant R and constant T surfaces. Let me erase this part. Okay, we just want to deal with the full maximally extended geometry, because if you want to cut it out, you can always cut it out, right? We might as well do the whole thing first. So first, let's look at the constant R surfaces, constant rho. Well, it's not surfaces. Let me write constant rho subspaces, right? Because we are putting one condition in on 4 coordinates. Okay, but for us, it's basically the T and R the rho coordinate that is the relevant one, right? Theta phi just goes along for a ride. Okay, so if you take constant rho, okay, we can see that this corresponds to R prime square minus T prime square constant. Right, because the right hand side is constant. Furthermore, this constant is positive for rho larger than 2 gm, and it's negative for rho less than 2 gm. So these are hyperbola. Okay. So let me draw some of these. But and all of these have asymptotes as these lines, these dotted lines. Right? Constant R prime minus T prime, as say T prime goes to infinity, R prime approaches T prime, right? So the asymptotes of this hyperbola are all these lines. Okay, so here also we have these, and here they're like these. So if, for example, we are observing the black hole sitting at a fixed distance from the black hole. We will be traveling around any one of these curves. Right? Imagine that we are far away from the black hole, sitting at a fixed value of rho, and observing it. We will be traveling along one of these curves. Is that clear? Right? Because constant rho means from in the Schwarzschild metric, we are at a fixed position, right? Rho equal to rho naught. Theta phi, I'm assuming, remains constant anyway. Okay? We are at a fixed angular separation. Okay. The next thing is to look at t equal to constant t. So for this, we can just rewrite this equation a little bit differently. I can write this as 2 times 1 over r prime over t prime plus t prime over r prime equal to tan hyperbolic t over 2mg. So this gives you t prime over r prime is a function of t. Yeah, because this is 1 over t prime over r prime. Right? T prime over r prime plus 1 over t prime over r prime. So you can solve, this is a quadratic equation in t prime over r prime. You can solve for t prime over r prime as a function of t. So this means that a constant t implies that it's constant t prime over r prime. Okay. So if t prime over r prime is constant, right? What kind of curves are these? These are straight lines to the origin. Right? So these are the constant time slices. Okay, so let me draw them. So the constant time slices will be like this. And here is the direction of increasing t. Now, one thing you see is that at this point, somehow time doesn't flow, right? You increase t, but it always passes to this point. That's a reflection that this time is not a good coordinate system here. T is not a good coordinate system here, right? Because t remains fixed at this point, right? As we increase, sorry, or t remains fixed at this point. As we change t, right, this point doesn't move. Is that clear? At this point, right, if you are at this point and you ask what value of t does it correspond? Normally in space-time, you fix a point that has a specific value of all coordinates, right? T, R, F, everything, right? But this is not the case here. You fix a point and you ask what value of t does it correspond? Right? It can be any value of t, right? Because these are the constant t lines. This side is basically going to t goes to minus infinity, right? For which it goes to, so let me plot that also. So t equal to minus infinity, right, corresponds to 2r prime t prime over r prime square plus t prime square is minus 1. Tan hyperbolic minus infinity is minus 1. Right? So this tells us that r prime is equal to minus t prime. That's this line. This is a line corresponding to r prime equal to minus t prime. So that means anywhere on this dotted line, right, except at the origin, corresponds to t equal to minus infinity. And t equal to infinity has 2 r prime t prime over r prime square plus t prime square equal to 1, and this corresponds to r prime equal to t prime. Right? That's this line. Okay, so let me write this. So this is the line which corresponds to t equal to infinity, t equal to minus infinity, and this is the line that corresponds to t equal to infinity. Is this clear? So all I have done is that I have used this relation between r prime t prime and rho and t to map out what the constant rho surfaces are and what the constant t surfaces are. Right? And what we are seeing is that at this point, okay, you cannot ask what is the value of t at this point. Right? It can be anything. Okay, because all t equal to constant lines pass through this point. Okay, anywhere between minus infinity and infinity. Okay? That just reflects that t is not a good coordinate here. Right? A good coordinate should have a property that if you change it, you should go to neighboring point, right? But here you change t, you don't move anywhere. The last point, yeah. Yeah, so normally if a good coordinate system means that if you change the value of any one coordinate, right, you go to a different point. Right? If you change it by small amount, you go by move by a small amount, but you still move. Right? Here what we are saying is that if you are at this point, right, and you change the value of t, right, you don't move anywhere, right? Because all values of t pass through this point. All constant time surfaces pass through this point. Okay? No, there's a problem here. The problem is that t is not a good coordinate. That's the problem, right? It's not a problem with the geometry. It's a problem with the choice of coordinate system. So this is another reflection of the fact that t you cannot use as a good coordinate system at that point, right? Which you knew anyway, right? Because in the rho t coordinate system, the metric becomes singular, right? And it's reflection of the fact that at rho equal to 2gm, if you look at ds square formula, right? If you change t, ds square is 0. Okay? That basically means that you are not actually covering any physical distance if you change t at fixed rho. Is this point clear? Any question?
The dotted lines that we have are seems that constant row surfaces and the constant t surfaces, they are kind of really parallel.
Exactly. Yeah, certainly. Right? Because rho equal to 2gm, right, is this surface. Right? And the point is there, at this point, t can take any value. Here t equal to minus infinity and there t equal to infinity. Yeah, it is related to the switch of space and time coordinate also, right? Because after this, we know that rho and t changes their roles. So all that it is reflecting is a rho t coordinate system is not a good one at the horizon, right? Which you knew anyway, but we see it explicitly when you map it out in the from rho t coordinate system to the r prime t prime coordinate system. No t line. Yeah, it goes like this, right? No, inside the true horizon, no. Right? As t goes from minus infinity to infinity, it covers these outside regions. Exactly. Yeah. Okay, now we'll use this picture to get some insight into the black holes. Okay. We have already seen the fate of the observer who goes in, right? That observer has to eventually reach the singularity, right? There's no way the observer can come out. But now we want to understand what will happen, right? If we throw in something to into the black hole, and we stay safe outside, and you observe it. Right? What are you going to see? Okay, that you want to throw in something in the black hole and you keep observing that object. One thing we already know from our previous analysis is that if we have an object sitting very close to the horizon, it will have infinite redshift because g rho rho, sorry, GTT, G00, or let me write GTT is 1 minus 2 GM over rho, right? And this goes to 0 as rho goes to 2 GM. So the same formula that we got earlier, right, to calculate the difference in periods between two clocks, right, will show that if we place a clock very close to the horizon, it will have infinite slowing down, right, because this G00 is going to 0. Okay. So you expect that if we throw in something, we'll see that object slowing down as we observe it from outside, right, as the object approaches the horizon. So we'll try to understand why that's happening in terms of these diagrams. Okay, where in fact you can see it without doing any explicit calculation, right? That's why this diagram is very useful. Okay, if you want to study what happens when you throw in something into the black hole. Yes.
Let's say I throw in something, so I'll see it slowing down, but it might as well have gone inside the horizon.
Exactly. Yeah. But it might as well have gone inside the horizon means what? It will at some point go into the horizon, right? But well, you will still, that's the confusing thing, right? There's no still, right? I mean, you cannot compare the time of that object with this object, right? And you can already see it in this, right? That the time doesn't flow here. The coordinate t that you are using, right, doesn't flow here, right? So this line, right, object will cross here, right? That will happen at t equal to infinity, right? Because that line is t equal to infinity. Okay? From the point of view of the observer who is falling in, right, proper time of that observer remains finite when you cross the horizon, right? So that's why this question of whether we still see it or not, right, is not the right one, right? You can only ask what do you see, right? Not what really is happening to the observer at that time. At that time, the observer still hasn't gone inside, right? Just because your clock has slowed down, right? So the observer has spent only very little time, but you are thinking from far away that it has spent a long time. That you can check, right? You can calculate, right? I will not try to do that, but yeah, you can certainly try to calculate that. If you are sitting stationary inside, right, it will look like the clock outside is running faster, right? But of course, you are not sitting stationary, right? You are moving along a geodesic, so the calculation is a little more complicated. But indeed, if you are just sitting stationary at the horizon, right, just outside the horizon, you will see that the clock outside is running faster, right? Because that calculation goes both ways, right? It's a ratio of G00 at the two positions, right? So it will G00 will come in the denominator instead of the numerator.
So in this box, depends on and say if we measure time.
Yeah, but the point is what you are measuring is always your proper time, right? So measurement is not coordinate dependent, right? You use your clock and that clock runs in your proper time. So that is a quite well-defined question, right? If you have a clock sitting stationary, right, at near the horizon and far away, right, how will the ratio of frequencies be between the two clocks? Far away, the proper time is roughly t, right, because it's 1 minus 2 gm over rho goes to 0, goes to 1 far away. Yes.
If I go near the horizon and come back, you guys will be old.
Okay, yeah, yeah,
I mean, is it true? Like I go sit near the horizon for some day, come back,
yeah,
and when I come back, you guys will be old.
yeah, it is true. Yeah, it is possible, right? Right? I mean, it's like you go in like this, you go like this and somehow come out, right? And some object outside is going. I mean, you spend much more proper time outside than near the horizon. Right? Because again, it's the proper time which decides your age, right? Not the coordinate time. Yeah, but yes, you spend, I mean, your frame, right? You spend the same amount of time. You're not going to gain much, right? Unless you are competing with the other people that who becomes older fast, right? I mean, from your point of view, you just stay whatever was your life, right? If you live for 80 years, you live for 80 years in your clock. Exactly. So when you come back, you will find maybe 800 years, right? That you have spent 800 years in the clock of where you started from. You have to accelerate. You have to have a powerful engine to make sure that you can go and come back. Right? Yes.
Cannot move faster than light, right? So the trajectories cannot be any.
Exactly. Yeah, yeah. Yeah. You cannot move faster than light. So you go close, right? And then you can go at most parallel, right? Okay. So you come, that's why you come back very late. Right? You have not spent that much time in your proper time, but that corresponds to a very late time in the t coordinate.
In solutions, do we see some structure where we are as compared to the clock opposite of what is happening?
No, I didn't get the question.
Do we see something of which is opposite of what is happening here and see something like that?
Yeah, it will get faster. I mean, if you go far away, right, spend your time there and come back, right, then you will find that you have, I mean, your clock has run faster, right? You spend 800 years there, right, and you come back and you find that that clock is only running 8 years, right?
I want to ask, like, say some flat regions there, that argument goes for that. Could there be an analogy of this flat space, something to the flat space in that region as time, even the flat space has slower time than that region? Are there certain regions like that, something opposite of a black hole?
Not really, because of the gravity is always attractive, right? So the gravitational potential will always be, I mean, if you have some mass distribution, right, then far away the gravitational potential is always larger than what you have near the mass distribution.
Can't really construct a mass distribution so that our distribution.
That's right. Yeah, yeah. Because gravity is attractive, right? Near the mass distribution, gravitational potential always will lower. Yes, yes. Exactly. Yeah. But here the point is, the idea is that you go close to the horizon, you stay there for a while, and then you return back. Once you cross it, you cannot come back.
Yeah,
right?
So then you can come back and get at the same pace and time, then compare your
Exactly.
like full distance.
Exactly.
That will be
Compare the how much your clock has run.
that will be the proper time.
Exactly. That's right. Yeah, and it's just that if you go close to the horizon, and then stay there for a while running your engine. See, to stay there, you have to run your engine, right? Because otherwise you are getting pulled towards the center. So you stay there running your engine, right? Your proper time changes by something, and then you come back. Right? And then you compare clock, you will find that your clock has run slower.
Geometrically, that is equivalent to comparing the length of the arc.
Yeah,
You just draw those trajectories.
exactly.
The length of the trajectory, comparing them.
Yeah, but the point is, to calculate the actual length of the trajectory, you need the information of the metric, right? Because this factor is there.
Then that is equivalent to having a clock.
Yeah, the proper length is the clock. Proper time is the clock. Right? Because clock always measures the proper time.
The best possible thing that you can do is travel close to the speed of light and asymptotically.
Oh no, but the point is, yeah, if you travel close to the speed of light, but as long as you have not gone to the horizon, right, you are traveling parallel to this, and you will cut some of these lines, right? Constant row line will eventually cut you, right? As long as you can run parallel to this, so you can meet the constant row line, right, where your friend is sitting, right, far away. So it is possible because these asymptotes to the 45-degree line, right, passing through the origin, right? So you'll always cut it somewhere.
That would be a geodesic.
It will not be geodesic. Yeah. Once you go here, then I mean, yeah, it will certainly not be geodesic. Time like geodesic through which you can escape.
So, and like, let's say I'm crossing with the
Yes.
I have always this small part, small thing which I can escape, right?
Yes.
But is it actually possible to have a time like geodesic?
Yeah.
Through which I can escape?
Well, yeah, you can. You have to basically run it sufficiently close to the parallel. It's because what you mean by escaping, right? You have to be able to extend the time to infinity, right? Yes.
Eventually it will cross the line.
If you constantly accelerate, right, then the trajectory actually becomes parallel to 45 degrees. This you can check, right? So you have to constantly accelerate, right? And then you become parallel to 45 degrees. So even us, right, we have to accelerate, otherwise you'll fall through, right? Well, if you are orbiting, then there's an apparent acceleration, right? If you are here, you are talking about constant theta and phi, right? So if you put something at constant theta and phi, right, it will fall inside, right? Only way you can survive is that you have to constantly radially accelerate outwards, right? Because something has to hold you in place. Okay, if you have orbital velocity, then that helps, right? But I'm assuming radial motion here, right? Theta phi motion I have ignored. So, but if you constantly accelerate, right, it is possible to avoid this way, right? Because if you this you can check even in Minkowski space, right? If you do constant acceleration, then eventually your trajectory becomes 45 degree with the vertical axis, right? It's as if you are following the light trajectory. Yes.
Suppose I am looking at a star which is I will never see its surface actually cross the event.
Yes, indeed.
So technically, I will never see it become.
No.
But still it would be a black.
Yeah, still it would be a black hole. Well, still again, still is a word you cannot use, right? Yeah, so from your viewpoint, there will always be something outside. It will never collapse, right? That's why when you say still it will be a black hole, right? No, still it will not be a black hole because in your time it will never be a black hole. What are the black holes that we are seeing? Well, we are seeing, we don't see the black hole. We see something that is close to which has formed the black hole, right? And what you observe are the behavior of other objects near the black hole, right? That's how you know that there's a black hole sitting there. And that doesn't require that the black hole, I mean, in your time, the black hole has actually collapsed and formed, right? Because you are basically studying the motion of other objects in the Schwarzschild geometry. Right? And for that, it's not necessary that you have to see that everything has collapsed into the horizon. That will never happen, right? I mean, it's clear from this picture. Because as things go towards the horizon, it slows down infinitely.
Black, that means anything like something has been sucked in. By the time ratio turns out to be infinite, like still surrounding it, why would we see a black?
Yeah, but the point, it is so faint, right? That you don't see it. So because the point is, it is true that you can never see a black hole forming, right? But because of this infinite redshift, right, the power that you keep receiving, right, becomes less and less, right? So it's as if nothing is coming out.
It also mean it is bumpy. It's not straight. The time it will take to reach that uniform, so that will also be like quite slow down.
Yeah, but the point again, once you go very close, right? Once it has gone very close to the horizon, even the fact that there is a bump, right, you will not be able to see it from far away. Every signal gets damped, right? I mean, any information from the horizon that has this infinite redshift, right, or a large redshift. And so, if you just think of the wavelength, right, if you think in terms of photons, right, the energy that a photon carries is inversely proportional to this wavelength, right? This E equal to h nu. So, if it gets redshifted, right, then basically means that the energy that each photon carries is becoming less and less.
One more question here. Say that you cannot see the horizon, you only see some trajectories of the objects in the neighborhood. That means that we can only see events in the first sector, let's say.
Yes.
I mean, we can only see events in the first sector.
Yes.
How is that information sufficient for us to identify that it's a black hole?
Well, the point is that the experimentalists are not the ones who want exact results, right? You can never get exact results in an experiment anyway, right? So you have to see that it's sufficiently close to what a black hole should give, right? And that's good enough.
Special happens when
Nothing special happens from whose viewpoint? From outside viewpoint, you never see that it has found a black hole, right? So, I mean, that special event you don't even see.
But you see the star disappearing.
Yes, that's because it's getting redshifted, right? You just get less and less light from the star, and slowly it will just disappear. Right? Event horizons are always like this, right? That you never see anything go beyond the event horizon, right? When you study cosmology, for example, you will see that all these objects are moving away from us, right? And you'll have an event horizon, and eventually, I mean, most of the objects in the sky that you see will be outside our event horizon, right? Which basically means that however hard we try, we can never reach those stars or galaxies, right? I mean, right now, for example, we can reach our nearby galaxies if we try hard enough. Okay? But that will be impossible after some time, right? If we start our effort after a while, well, after billions of years, right, then you'll not be able to reach those galaxies. But we'll never see that those galaxies are out of our view, right? We'll see that they are becoming fainter and fainter. And we can do the calculation and we can see that now if we start, we'll never reach there, right? But we'll still be able to see those galaxies in a very faint form. Right? So event horizon, by the very fact that you cannot receive signal from beyond the event horizon, right, means that you can never see actually the event horizon forming. Right? Because if you could see it forming, that means you are receiving signal from the event horizon, right? Which you know is not possible. So that's why it's somewhat strange, but that's how the life is, right? I mean, general relativity is like that. You have to learn to live with it, right? Exactly. Yeah.
There is other ways of
Yes.
there is such a black hole and there is one
Hmm.
star collapse. You won't see the difference.
No, because the star collapse, I mean, after some time, as I say, will not see any view, will not get any information anyway, right, from the that system. So for all practical purposes, you will not see any difference. Exactly. Yeah, yeah. If the black hole has formed sufficiently long time ago, if the collapse has started sufficiently long time ago, right, then there is no experiment that you can do to distinguish.
The formation of a black hole from a collapsing star, what kind of effect does that have on the surrounding? Is there any special effect, for example, like some strengthening of accretion or something is observed?
Well, if it's a spherically symmetric collapse, then of course nothing will happen. You will not see anything, right? Because outside you will only see the Schwarzschild geometry, right? It just collapses and forms. But typically what happens is that there is, I mean, it's not spherically symmetric, right? There is a rotation. And then there are accretion and various other things that happens during the collapse of the black hole. Right? But that requires more detailed study of hydrodynamics at the of the collapsing star, right? What kind of accretion you will have during the collapse of the black hole. Compare, yeah, exactly, exactly. Yeah, you can think of black hole as an internally collapsing star. Right? This is the ones that you know of. It need not be star, right? What the black holes at the center of galaxy are probably formed by collapsing just the dust, right? The protons, right? They basically collapse and form the black holes at the center.
Say about like detailed study of hydrodynamics.
Basically, you have to look at what is the equation of state of the matter that is collapsing, right? And combine that with the effect of gravity to see what kind of motion it will have, right? So it's basically a detailed study of the motion of the, you think of this as a fluid, but fluid subject to the influence of gravity, right? And then you have to basically simulate what kind of evolution it will have when it's collapsing.
Just to try to understand, when you have a collapsing star and just forms a black hole, the metric and the gravitational strength around the space-time is more or less remains the same, right? It just cross the event horizon.
Exactly. Yeah. Because the crossing the event horizon, right, is a very mild affair, as I said. If it's a big black hole, right, then you can calculate the Riemann tensor at the horizon, right? And for large enough m, it will be a very small effect, right? So the crossing the event horizon is not a major affair, right, from the actual collapse process. But to actually fully study what's happening there, right, we have to solve hydrodynamics.
When we take into consideration the energy moment and finite size of the star and everything, still the picture still holds.
Yeah, the picture still holds. It says that this picture is, as you can see, that when you have a collapsing star like this, outside the geometry is exactly Schwarzschild, right? If you don't, as long as you assume spherical symmetry. Inside, of course, the picture will change. Right? Just like if you have a star, right? The inside the star, the gravitational field is not 1/r. Right? You have to take into account the mass distribution inside.
Outside whatever we said.
Exactly. Outside whatever we said will still hold.
When we describe the situation of observer accelerating near to the event horizon, what will be the effect of this acceleration of spaceship on the edge of?
That you can calculate, right? You don't even have to say explicitly the acceleration of the spaceship. You can calculate the proper time. Right? You take any trajectory which need not be a geodesic, and the clock, the how much time the clock registers will be based on the proper time that the clock spends. Right? Assuming that the clock is resistant to external pressure, right? Non-gravitational pressure, right? That you have assumed anyway. So you have prepared a clock so that acceleration of course means that there is an external pressure, right? As long as those things don't affect the clock, right? That depends on what the clock is made of. Right? Just the gravitational effect you can calculate by taking into account the proper time along the trajectory, that how much proper time you spend. Is this okay? Okay, so let me just do this geometric analysis. How we see this? I think a lot of it has already been discussed. Oh, yeah. Thank you. Yeah, let's draw this picture again. So now suppose that we have something falling into the horizon. Okay, we have already seen this redshift effect, right? But can we understand this geometrically, right? Why is there a infinite redshift? And this again we discussed, but let me say it again. Then imagine that you have some observer at fixed row, right, far away, who is observing this. As it falls in, it keeps emitting say light, right? That's how you see it. And the light travels at 45 degree, right? Assume that it's radial, so that you don't have to worry about the theta phi direction. So the light keeps traveling like this. This one is the observer. This is the observer, fixed row, right? That's the hyperbolic line. And this is the falling object. Okay. Observer has to accelerate. I mean, if you are at a fixed radial position, right? But that acceleration can be small, because if you are far away, you only accelerate a little, right? To make sure that you don't fall in. Okay, so sorry, this should be 45 degree. I have not drawn it perhaps correctly. This is now for this observer, if as long as rho is sufficiently large, the proper time is t, right? Roughly. Ignore this 1 over 2gm minus 2gm over rho factor. Proper time is roughly t. So we want to know that as this is emitting this radiation, okay, when are we going to collect that radiation from here? Okay. So to do that, you have to calculate the t values here, right? But the t values you know how to calculate, because you just draw the straight line. I draw a different color. To find the t values, we just draw the straight lines from here. Right, because constant t lines are the straight lines to the origin. Okay, so this, by knowing the slope of this, you will figure out what the t value is, right? And let me write this again: 2r prime t prime over r prime square plus t prime square was tan hyperbolic t over 2gm. But just from this picture, you can see, okay, that as the object is going closer and closer to the horizon, okay, the slope of this line is becoming more closer and closer to 45 degree. Okay? And the 45 degree line is t equal to infinity. Okay? So from this observer's viewpoint, when the observer crosses the horizon, okay, that reaches the asymptotic observer at t equal to infinity. A little earlier will reach before t equal to infinity, but a very large time. Okay. So this is a pictorial way of saying why we'll see the object slowing down. Okay. Because as the object is falling into the horizon, right, the time that at which you are observing it becomes later and later. Right? It just gets stretched out. So this is the explanation. So the pictorial explanation. So this is a pictorial explanation of the slowing down. Okay, and all this I have drawn, even though I have drawn it in the two-sided black hole case. You can also draw this in the single-sided case, right? All you have to say, make sure is that this object that is falling in, right, is after the black hole has collapsed, right? So this is a collapsing object. This is a star. As long as the other object that is falling behind, falling inside, is behind the star, right? Behind the star, okay. After the star has collapsed, right? You can use this picture still. So, in other words, right, this infinite time delay, right? You can say, oh, black hole never forms. So how can you see infinite time delay? Right? The point is that's not necessary. As long as the object that you are throwing in, right, falls after the black hole, after the star has collapsed, right, you will see this infinite time delay, right? As you go, as it goes closer and closer. Because outside there is no difference between the short cell solution and what you have for a collapsing star. Is this clear? Yes.
This infinite time we are saying, I mean, generally we say in physics we talk about order of time, right?
Hmm.
So this is infinite compared to what order?
Well, it's infinite measured in your clock, right? Now imagine that this object has been instructed to send pulse every 1 second.
That 1 second will become infinite.
Exactly, that 1 second will become infinite, right? If it's near the horizon. That's what this is saying.
That pulse will be that will be the proper time of the falling.
Yeah, exactly. So if you have set the infalling observer so that in its proper time, it sends a signal every second, right? And the observer who is far away, right, that observer also measures it in its proper time, right? And that proper time, okay, will become infinite from the far away observer's viewpoint. Any?
Going back to gravitational redshift,
Yes.
the only reason was proper times different at different places.
Yes.
He has special.
Exactly.
What's happening? It's just an extreme case.
Exactly. Right. I mean, here this is a little more general because there we did the calculation assuming that the objects are stationary, right? But from this picture, we see that it's not necessary that this is stationary, right? It's just falling in. Still, the signal that we receive from there is getting infinitely stretched. Exactly. Yeah. Then that time you are comparing two constant row slices, right? And the proper time here will be stretched compared to the proper time. Right? Here you are talking about not a constant row slice, but something which is going closer and closer to the horizon.
You write the geodesic equation from massive part. It's the same part.
Yes.
How can I see that?
Okay. I mean, you cannot see it in this diagram because the theta phi I have taken constant, right? This is only describing radial motion. To see that, you have to actually also include the other coordinate, right? At least the phi coordinate. Yes, that you can do. But I have assumed that this is theta and phi remain constant. So the geodesics that are drawing, right? We are assuming that it's happening at constant theta and phi. These light cones, for example, that you have drawn, right, are all at constant theta and phi. So if you want to describe radial motion, this is good. These pictures are good. Okay. If you want to describe the motion of the planet, right, that will be hard to describe here. Because there, not just r is changing, but also theta is changing, right, or phi is changing. Is this clear? See, even in Newtonian gravity, right, the radial motion is very different from the orbital motion, right? Orbital motion have this periodic orbit. Radial motion is either you run away to infinity or you go up to some distance and fall back. Yes. Yes, exactly. So geodesics will basically roughly look like this. Yeah, you can work out the details, but roughly it will look like this here.
But for a planet, it should be a elliptical orbit almost.
Yeah. So these are all only radial geodesics. See, in this picture, you can only draw radial geodesics.
That should look like it is, I think, switching between two constant flows.
No, but that requires that d theta dt is non-zero, right? Or sorry, d phi dt is non-zero, right? D phi du is non-zero.
There will be some contribution going to those.
Exactly, that's right. That in this ds square expression, right? You also have this d theta square and d phi square, right? We have all these the light cones and all that we have drawn, right? We have assumed the theta and phi are constants.
So if we have a finite infinite test,
Yes.
then we just looking at the r prime p prime coordinates, seeing that particle or whatever the object is accelerate, right? We'll see some acceleration in this here.
Yes, indeed, that's right. That's indeed it will oscillate in the once you take into account non-zero d phi dt, right? It will oscillate between two r's, two radial values, right? Which means oscillate between two of these constant rho surfaces.
But what you are drawing the observer here,
Yeah.
That's a stationary observer, radially stationary observer.
Exactly.
Not assuming any defect.
Exactly, that's right.
This trajectory is something of a particle who is not changing in theta and phi.
Exactly.
That will fall into the for sure.
That will surely fall into the black hole unless you accelerate, right? So this one is not a geodesic, right? You have to put an acceleration to stay there.
Yeah, so there will never be a geodesic sort of oscillate this diagram.
Yeah, well, you can plot it in this diagram if you want, right? Then you take the original the solution that you have found, right?
It will require acceleration, right?
So that's coming from because the phi motion is there. That phi motion is providing effective acceleration, right? But if you don't plot the phi, it will look like it is accelerating, right? In this diagram, it will look like it's accelerating, right? But that's because there is a phi motion. Right? I mean, after all, I mean, when you have a planetary orbit, right? I mean, you can ask the same thing. Suppose you are trying to describe it as radial, only in the radial direction. It looks like radial direction is going back and forth, right? So what is causing that motion, right? Without acceleration, right? And that's because of the orbital motion, right? That is providing the effective acceleration, right? Or the pseudo force that is making the radial direction going back and forth, right? So it's the same thing here. Yes.
You talked about neutron stars, so it's also like collapsing star,
Yes.
right? So, but we can observe neutron star and pulsars. So, what are we actually observing at this? Because basically, not it will take infinite time.
But the neutron stars are not black holes, right? So their horizon, their size is larger than the Schwarzschild radius. So that you can certainly observe, right? It's only when the size has become smaller than the Schwarzschild radius that is something that you cannot see, right? So neutron stars you can observe as just as you observe the surface of the Earth, right? I mean, because the actual horizon size of the Earth is much smaller, right, than the surface. So as long as the radius or the surface area, the surface is outside the horizon, then you can observe it exactly, right? There is no confusion. So neutron stars are like that. You are observing actually the real surface of the neutron star. Right? It's only when things collapse into a black hole that there's an observational problem. Is that okay? Or okay, here you are not doing quantum mechanics, right? This is pure classical gravity. So there's an uncertainty principle. Of course, in quantum gravity, you have to worry about all that. Yeah, so quantum gravity is quite different. Well, not quite different. It will be approximately this, but then you have to take into account the quantum effects. Well, it becomes even more confusing, right? Because there you find that the black hole starts radiating, right? Instead of that, here you saw that nothing can come out of the black hole, right? Once the black hole has formed, it just remains there. In quantum gravity, you find that the black hole starts radiating, right? So it's certainly more confusing there than in classical gravity. Any other question? So let me just mention the other black holes which are known. Okay, so generalizations. Okay, we can have black hole carrying charge. These are basically in the order of difficulty. Okay, so this will be in fact there will be one homework problem on this, on charged black holes. Electric charge. Right? The black hole. Basically, you have to solve the combined equation of Einstein Maxwell. Okay, but once you impose spherical symmetry, it's easier. Okay, so I'll set it up properly, right? So that it will not you will not have to do too much work. Then we have rotating black holes, right? Black holes with angular momentum. These are much more complicated. These are complicated because once you have angular momentum, you cannot apply use spherical symmetry anymore. Okay. What you can do at best is azimuthal symmetry. Okay, because the angular momentum is along some direction, so you have azimuthal symmetry around that direction. So the equations are much more complicated, but this solution basically all the black holes that we have observed are described by this solution. Okay, because typical black holes do carry angular momentum, okay, and they don't carry charge, right? Because putting charge inside a black hole is quite difficult, right? Because of the fact that in the universe, right, matter is neutral, right? There are always the kind of objects that you see, right, have equal amount of protons and neutrons, sorry, protons and electrons, right? So that there is no net charge. So typically, when you form black hole out of collapse, you don't put charge on the black hole, right? Even if you put some charge, it's so small that it doesn't matter. You don't see the effect, right? But the angular momentum you do put. Typically, when you collapse matter, you do impart angular momentum. So this is basically describes most of the black holes that you see.
So the magnetic field is very important.
Yes. That information basically goes away once the black hole has formed, right? Then the magnetic field that is happening is because of some motion inside the horizon, right? And that information doesn't come out. So if you have black hole with charge, rotation and charge, right, that can have some magnetic field. Okay, so that's the other case. Black holes with rotation and charge. Okay, again, these are very rare because putting charge is very difficult. Okay. But the solution exists. Okay. If you have black hole with rotation and charge, this will have magnetic field, right, because these are moving charges. But as I said, these are more mathematical solutions, right? They are useful for various theoretical studies, but for all practical purpose, right, this is the solution that we really need, right? The Kerr solution, which is the rotating black hole. No. Charge and rotating, it will radiate at a classical level, meaning electromagnetic radiation. Yeah, electromagnetic radiation may happen, yes. Okay, maybe I should put it this way, that the Kerr solution, right, or this is Kerr-Newman solution. Kerr-Newman solution will not radiate because it's static. It's rotating, but it doesn't have time dependence. Okay, it's a static solution, right? So it has no radiation, right? Neither gravitational radiation nor electromagnetic radiation, because they're exact solutions to Einstein's equation or coupled equation of Einstein and Maxwell. If you try to throw in something, then there will be radiation, right? But not this Kerr solution itself doesn't radiate, or the Kerr-Newman itself doesn't radiate. Okay, any question? Yes. Classically? Yeah, so this doesn't radiate. Static solutions don't radiate, right? If you are moving, if you have time dependent objects, then the radiation may take place from outside the horizon, right? Because gravitational field and field is changing, right? And that can give out gravitational radiation. Not electromagnetic radiation, because electromagnetic radiation requires charged particle outside, right? But gravitational radiation can take place if there is a time dependent gravitational field.
This charge or not, the effects would be conveyed.
Charge you cannot screen, right? Even the horizon cannot screen charge. Okay. So that's the only information which can come out. Okay. Because charge is a conserved quantity, right? Imagine that a charged black hole, a charged system is collapsing, right? You can measure the charge from far away by Gauss law, right? By integrating the electric field at infinity. So even after the thing has collapsed and formed the horizon, right, the Gauss law you can keep applying. Right? That information doesn't go away. Yeah, mass of the black hole, for example, is information that you can see. Charge, mass, and angular momentum are the most general characteristics.
Let's say before collapse, the star or the collapsing object has some sort of asymmetric distribution.
Yes.
Yeah,
symmetrical distribution of charge also you can see from infinity, because you just integrate the electric field, right?
Yes.
Over the surface at infinity. And that tells you what the total charge is.
Yes.
Right?
Then if it's asymmetrical.
No, once it has collapsed into a black hole, you will not know.
All that information.
All that information will go away.
Charge is still.
Exactly. Information from total charge will still be there.
Same for mass, right?
Same for mass, exactly.
We had some sort of symmetric distribution.
Yeah, it will be wiped out by the time it has formed the horizon. Total mass will be there. Information will be there. I think Kerr-Newman is the most general solution, which is azimuthal symmetry and time transition symmetry, right? All these are time independent solutions. Stationary, yes.
After it has collapsed, the electric fields will never exist.
Yeah, so electric field will remain, right? No, it will escape. That's the point. After it has collapsed, right, the electric field information, right, see, it's not sending signal, right? Electric field was there to begin with, and it will remain after the collapse, right? Is that if you now after the collapse, right? Suppose somebody goes inside and changes the charge distribution, right, from spherical symmetric to non-spherical symmetric, that information will never come out, right? But the total charge, somebody cannot just go inside and decide that I'll change the total charge, right? The only way to change the total charge is the person has to carry the charge, right? And then that information will be there again at infinity, right? Because you see it from as electric field at infinity. So information on the charge cannot be erased, right? Similarly, information on the mass cannot be erased, but other information will be erased once you go into the black hole. What? Classical, yeah, everything is classical, right? We are not doing any quantum gravity here. Yes.
We can measure charge, we can measure mass by
Gauss law.
measuring gravitational field. What about angular momentum?
Angular momentum also there is a way to measure, right? There is a formula for the angular momentum which is more complicated, but it is possible to measure by looking at it infinity. That's the reason why Kerr-Newman, the Kerr solution exists, right? Because you can detect angular momentum at infinity. Because that's also in a sense a conserved quantity associated with rotational symmetry.
That means that we can only see quantities that provide.
Yeah, whose information you can obtain at infinity.
Describe what actually is a black hole.
Anything which has event horizon, one-way membrane, like a one-way membrane, right? An event horizon is something so that once you go inside, you cannot send signal back. That is what is the general definition of black holes is that it should have an event horizon, right? So that beyond that, right, you should not be able to send signal back to infinity.
Whole mass of something is less than 4 gm.
If the radius is less than 2 gm, yes. If the radius is less than 2 gm, that will form a black hole. Indeed.
Here you said that the future of this star is to form a black hole,
Yes.
but we did not put any restriction on the mass.
Oh, because okay. Of course, in practical situation, there is a limit. There is the mass has to be larger than something. Because what happens if the star starts collapsing, right? There are various nuclear and electromagnetic forces that are acting, right? And that pressure prevents the star from collapsing, right? Only if it exceeds a certain value, you can show that other kinds of interactions are not able to hold the star back. Right? The gravitational interaction becomes so powerful that it keeps collapsing, and eventually it forms a black hole because the radius of the star becomes less than 2 gm. Any mass wouldn't form a black hole. I mean, Earth, for example, right? You leave it as long as you want, it will not form a black hole. It's a question about density. See, initially the density can be low, right? But then the gravity is pulling things inside, right? And then there is some other kind of forces which exerts pressure, which is keeping it apart, right? Eventually, suppose the star runs out of fuel, right? Right now, sun, for example, exists because there is a thermonuclear reaction going on in the sun, right? Which is keeping the sun, preventing everything from collapsing. Suppose that thermonuclear reaction stops, right? Then things will start collapsing. But nevertheless, there will be pressure due to the material, right? Because you can't pack things too hard, right? Earth, for example, right, is not collapsing because interaction between the molecules inside the Earth, right, are pushing it back. Right? That's why Earth is not collapsing. So in order for it to collapse, right, even after the thermonuclear reaction has stopped, the gravitational force has to be sufficiently big so that this other kinds of pressure cannot prevent the collapse, right? And that requires a mass of certain size, right, beyond a certain size. These things, no, probably not, right? I mean, that's more a course on astrophysics, right? The formation of the, depending on the initial mass of the star, right, there are various fates that it faces, right, including neutron star, for example, right, which is not a black hole, but where everything collapses into neutrons, right, in a big ball of neutrons. You need bigger than that to actually form a black hole.
This is the mechanism here. Because we know how, what kind of forces, what kind of interaction.
Exactly.
Keep a star.
Yeah. Right. We have to know the nuclear physics very well,
Yeah.
right, to be able to see whether it will eventually form a black hole or not.
Can electromagnetic forces take over gravity? And if they don't, this collapse.
Exactly. Right. So you have to make sure that the gravity is strong enough so that the nuclear and electromagnetic forces are overcome, and then gravity keeps shrinking the star.
If there is some other interaction.
Yeah, if there is some other interaction, right, you're right that, I mean, of course you don't know all the interactions, right, but as long as those interactions become important after the you have gone below 2 GM, then those are not important, right? So because those interactions may become important when the densities becomes too large, right? But suppose it has already collapsed below 2 GM, then it doesn't matter if those other interactions take over.
Okay, so if an interaction which we have not yet observed, it would certainly not affect.
It will not affect the black hole formation, right? Because what will happen is that as this is collapsing, right? So here is the picture. You have the surface of the star collapsing, right? This typically is not a geodesic because there is a pressure inside, right, which is preventing it. Okay? But you know that as long as it forms, okay, then it doesn't matter what you do, right? It will eventually hit the singularity. Right? So those interactions, what will happen is it will probably change the trajectory of the surface inside, right? Because it will try to push things out. But even if it tries to push things out, eventually it will have to hit the singularity. Okay, so
When it pushes things out, we cannot exit that.
exactly, you cannot exit that horizon anymore.
Whatever, I mean,
Once the horizon has formed, you cannot exit.
But it can certainly alter that.
Yeah, it can alter this surface. Yeah, indeed. So it can alter the trajectory.
That limit we have 1.44 marks.
Yeah.
That will be altered. Right?
No, that will not be altered because that only requires that you overcome the nuclear forces to form this, right? If those other forces become important after this, then it will not help you prevent the collapse, right?
by then the black hole is already formed.
Exactly. By then the black hole has already formed, right? It will alter the trajectory of the surface of the star inside.
And if it affects the dynamics, that is not exit.
Exactly. Exactly. Yeah. Exactly.
Same argument with both idea has
Exactly. Yeah.
same.
Yeah. Because it will be screened by the horizon, right? Before, yeah, exactly, right? But that, of course, we know. I mean, so because the fifth interaction, if it happens, it has to happen at a very short scale because you have explored all these accelerators are trying to look for all kinds of interactions, right? So you know that there is a limit on when that fifth interaction could take place, right? And that will not help because before that the horizon would have formed. How have we explored it? The accelerators, right? The accelerators where you collide particles at very high energy, right? So that you put them at very short distance and you see what kind of scattering that takes place, Right? That's how you explore what kind of other forces there are. Yeah, so the point is, to that extent, we know the standard model works quite well, right? And all those forces can be taken into account, and it doesn't prevent collapse.
Whatever the result coming from this, just we can apply for a star.
For a star, yes, indeed. I mean, the point is, if you are not connected, interested in the horizon physics, right? Then even for a star, right, the field outside is a Schwarzschild metric. So you can certainly use Schwarzschild metric for studying what happens outside the star, right?
And in that case, for example, a neutron star and the magnetic field is very important.
Yes, indeed.
So over there, that also we will include through the FPU.
Exactly. Yeah.
And related to this, for the electromagnetic radiation, can the electromagnetic radiation cannot escape from the
Inside, yes.
But if some electromagnetic radiation is arising, that will be due to the dynamics happening outside the horizon.
Yes, indeed. So, but for that you need charged particles outside, right? See, unlike gravitational radiation, which can happen without charged particles, because gravity is non-linear, right? Gravity can act as its own source of radiation. This doesn't happen for electromagnetism. Okay, so if you want to get electromagnetic radiation from a black hole, right, you really need charged particles outside the horizon. Pardon?
GW related to gravitational, of course, that escapes this event horizon and all.
No, it's outside. It's not. It doesn't come from inside the event horizon.
It's coming from outside.
From outside, yeah. Right? It's like when two black holes are spiraling, right? Each has its event horizon, but outside there's gravitational field, right? And that's what is producing the gravitational radiation.
When we talk about measuring the mass of black hole, we generally do by observing the velocities of surrounding objects.
Exactly. Yeah.
And similarly for charge.
Charge, as I said, I mean, we don't know of any black hole which has charge, right? If you have charged objects, for example, the various plasma rotating around the black hole, right? You can observe, I mean, by studying their motion, you can figure out what the charge of the black hole is.
Electromagnetic radiation can't be, but the electrostatic field would be there.
Yeah, exactly. Yeah. The electrostatic field doesn't carry information, right? If you start with a charge Q, it remains charge Q, right? So you are not transmitting any information across the horizon.
Distance of the charge is conveyed. There is a charge.
Yes, indeed. And because that will measure the electric field at infinity, integrate, and that will tell you what the charge is. Yeah, that was the idea. That I'll start cosmology, of course, in this course itself, and then in the next semester I'll discuss more advanced.
Study a star which is collapsing, and if there is an object which is say accelerating along with the star, some observatory which is traveling along with the star, and eventually the star is first going to go the horizon. So till that time, can get the signal for that, can send the signal to for outside.
Yeah.
In that way, we can do the experiment.
But it will not help, because if the signal comes from here to us and then you transmit it outside, right? That cannot go faster than the direct light signal, right? Because I mean, you are just combining two trajectories, right? Which are both either space-like or light, either time-like or light. That's, I mean, that was worse than direct signal.
I thought the T goes to infinity happens as we go near to the
Indeed. But the point is that the signal from here cannot go more than 45 degrees. That's the universal, right? Imagine that you have some object here, another object here. You transmit, and then that object transmits, right? But that is the same as you might have to directly transmit, right? So each of these are less than 45 degrees. Yeah, right? So you could have directly transmitted around that.
Anyway, the light has to take equal speed.
Yeah.
If I try to do it, will become this.
Yeah, exactly. I mean, if you have to, I mean, either it will remain the same or it will become one. So if you try to catch the signal from another observer, right, and then transmit it back, you are basically spending some time in processing the signal. I mean, otherwise you have not assumed that the signal gets repeated or something. You are just calculating the time that it takes. And for that, a direct path is always